Alright, this should be going out live now. Let me just check things. Make sure things are working. Looks like it's working. Yep. Cool. Pop out the chat. Alright, welcome to Astronomy Live. So tonight I'm going to be doing a live stream here talking about some of the latest data I've got on the Tesla in deep space. The SpaceX Falcon Heavy launched a Tesla into deep space, out of Earth orbit, into an orbit that takes it slightly past Mars's orbit around the Sun. And over the last 8 days or so I've been taking pictures of it using a telescope in Australia, which you can see conveniently enough positioned behind Starman in this picture that Elon Musk tweeted of Mission Control an hour and 23 minutes after the launch last week. So we're going to talk about that, and we're going to do a simulation of the launch and see if we can fit that to the orbit that the object seems to be in. We'll see if that's consistent with the telescopic images. And I'll discuss how I know that it really is the second stage of the Falcon Heavy. Alright, so we're going to get into it here, but I do want to say that this first part of the stream, we're going to be talking about the actual pictures and some of the data, and I'm probably going to split this off into a separate video afterwards as its own upload, because I think for people who just want to get the gist of the data and what the numbers show from the actual telescopic images, this can make a nice, brief, relatively brief summary of that. But we're going to keep streaming after that to do a simulation of the launch, and I'm going to see if I can get it to simulate the whole webcast, the Starman webcast that SpaceX put up for several hours after the launch. When they did that, the second stage was in a parking orbit of sorts. It was in an elliptical orbit that took it as close as about 190 kilometers from Earth's surface up to about 7,000 kilometers from Earth's surface. And after about 6 hours, they ejected it from Earth orbit, using a final burn of the second stage to push it out of Earth orbit all the way out to Mars and even slightly beyond. And so we're going to get into that now. So this, as I mentioned, is a photo that Elon Musk tweeted out shortly after launch. You can see the mission timer up there at the top, 2045. That's universal time actually for when the launch actually occurred, at 8:45 p.m. universal time, or 3:45 p.m. Local time, Eastern time, where I was viewing the launch. And you can see the timer above that, 1 hour 23 minutes 27 seconds. And so if you do the math, that seems to indicate that the image occurred at 22:07 and 27 seconds universal time. And so we'll see if that matches up with the simulation. And I should probably check on the simulation. So it's actually counting down right now. I can pause it if I need to, but we'll get to that in a minute. I've got about 23 minutes till launch on the simulation. So let's get into some of the images. So this is an image I took of the Tesla and second stage in space earlier today using a telescope in Australia, T27 on the iTelescope.net network. This is a 0.7 meter telescope. In other words, its aperture is about 28 inches, which is quite significant. It's quite a powerful telescope, just about the most powerful telescope you can rent anywhere. And you can use this telescope, you can specify where you want it to point and what you want it to take pictures of. And what I had to do is I had to take pictures of the Falcon Heavy second stage in deep space. Now, according to my calculations, it was over 7 times farther than the moon at the time that this picture was taken earlier today. In fact, it was almost 7.8 times the Earth-Moon distance at that time. And using SAO image DS9, I'm able to pull the coordinates for the object in that image. And I took 4 images today, so I'm going to go ahead and blink those so you can see them in motion. So there you go, and the times and universal time are listed there as well. Now, using that information, I can solve for the orbit. And I did this in an earlier video about 8 days ago, and I'm able to add the current data from today into that solution and produce a better solution. The first day I tracked the Tesla and the second stage, I only had about an hour's worth of data, and so that's a very short arc to cover the orbit, and so the orbit's going to be fairly uncertain. There's going to be a certain degree of uncertainty in that orbit solution. But as you cover more of the orbit, as you cover more time, the certain uncertainty goes down. You don't need a drastic number of observations as much as you do time. Time is a precious commodity when trying to nail down an orbit. The more time you can cover, the better, which makes it challenging when the object is getting progressively dimmer and dimmer. When I first imaged it about 8 days ago, it was within grasp of many amateur telescopes, but now it really does require a very powerful telescope to see it. So this 0.7 meter telescope can see it, but as you can see, it's a very dim little dot. And this has led some people to question, how can I possibly know what that dot really represents? How can I possibly know what that is? In fact, it's so dim, it may be coming across rather poorly on the stream. So let me just pop on a blown up view here. Let me pause this. Okay, and I'm going to turn on a slightly expanded and slightly contrast enhanced view here so you can see that. Now it might be a little more clear, but you can still see it's a very faint object. And so how can I possibly know what that is? Well, obviously the identification is not taking place based on the shape. You can't resolve the shape of it that far away. It's much, much too far away for any telescope on Earth or even Hubble to resolve it as more than a point-like light source, meaning looking like a star that moves. And that's what we see here, but we can trace the orbit, and that can tell us some very important information here. And so I'm going to show you guys what that actually tells us. So this is the orbit solution. This is all of the data I've collected so far. So from February 8th all up to today, including some observations I did on February 13th as well, we have a pretty good orbit solution here from just 20 observations, enough to make certain determinations. For example, on the left side, you'll see a box above the white box that shows you the orbit elements relative to the Earth. And you can see perigee occurred on February 7th at about 2:36 universal time, give or take. That means that's when it was last closest to Earth. And that distance, if you look at the little Q, says 6976 and change. That's in kilometers, and so that's from the center of the Earth. In other words, it was less than 1,000 kilometers from Earth according to this orbit at about that time. And you can see that the eccentricity E is 1.2 and change. In other words, it's hyperbolic. It's ejected from Earth orbit and it's heading out into deep space. The inclination, 28.6 degrees, that's a very familiar number to me because that is the latitude where I grew up in town, just near the Space Center. And that happens to be the latitude of the Space Center and the launch site. And that's not a coincidence. They launched the Falcon Heavy with a heading due east of 90 degrees, and that means the inclination relative to Earth takes on the latitude of the launch site. And so as you can see, if I solve for the orbit, it tells me this thing came from Kennedy Space Center. So, you can also see on the right side, highlighted in blue, a particular point in time and some particular coordinates for MPC code 696, which corresponds to the location of the MMT observatory. And the reason I've pulled that up is they have this video here from MMT, and they actually caught the second stage doing its final burn, ejecting from Earth orbit on the evening after the launch. And so I'll play this little time lapse here from their all-sky camera. So let me come in here. Let's see, let's make this theater mode so it's a little bit bigger. And I'll go ahead and play this video. And so on the right-hand side, near the west direction, you can see a large white ball, and that is the second stage. I'm suspecting that they've already done a ullage burn there to push the fuel towards the bottom of the fuel tank. Frequently with vehicles like this, they have to basically induce a little bit of thrust to shove all the fuel to the back of the fuel tank so that when they engage the engine, there's fuel in the lines and everything flows properly. And so at that point you would expect to have a bit of a cloud around the vehicle from that initial thrust. But they haven't actually engaged the engine just yet. You'll see it when it comes on. It really starts to lengthen out a lot more. And you can see the time up at the top was about 7:30 local time, which was about 9:30 Eastern time where I was at. So here in a second you'll really start to see it suddenly grow. There it goes. It's starting to grow bigger and bigger and bigger. And so that's actually doing the burn there. And right here in a second, right there, it shuts off. And so that was the end of the burn. You can see a little bit of a streak just at the tip of where that large white area is. That large white cloud is the exhaust from them doing the burn that ejected it from Earth orbit. And that was at about 9:32 Eastern time, or about 7:32 local time there at the MMT Observatory in Arizona. So I've actually done a measurement of this, and you can see that here. And basically I just took this image into GIMP and measured out how far that little streak was right as the engine shut off from the center of the image, or the zenith, the point highest in the sky, and also the angle. And you can see that there at the bottom it was 503.3 pixels from zenith. I also measured before this point the distance between a couple of known stars, Rigel and Capella, in order to determine the image scale. And according to my calculations, the image scale is roughly about 8.5 pixels per degree. Now, all sky cameras like this do have a lot of optical distortion, so it's not going to be perfect, but if you do the math, it actually comes out pretty well. So let me go back to the orbit here in that blue line I've highlighted there. So you can see a couple of numbers of importance here where it says plus on the right, towards the right side, it says plus 27, then a space, then 196. That's the altitude and azimuth that my orbit calculation predicts the object I detected and tracked to be at that very time. At the time that burn was occurring, my orbit predicts that it was about 27 degrees high and at an azimuth of 196, right as the burn shut off and where that picture was looking. So let me turn off the orbit again. So again, I measured it using GIMP, and using that measurement, it comes out to be about 31 degrees altitude based on the distance from zenith. You can subtract that from 90 to get the altitude over the horizon, and then the azimuth based on the angle there of 77.84 degrees. If you subtract that from 270, that tells you what the azimuth angle was, which comes out to 192 degrees, so 12 degrees west of due south. And so that's within about 4 degrees of the predicted angle in both altitude and azimuth. So again, based on the orbit that I calculated, if you trace that back to this moment in time at that observatory, it should have been visible in the sky at right about that position. So that tells me that's the same object, which is no surprise because this is the Falcon Heavy second stage performing its final burn. So again, it all matches up. It came from Kennedy Space Center. The time there at perigee, 2:36 Universal Time, or about 9:36 Eastern Time, so within a few minutes of the observed burn time. That's when it was last closest to Earth, and the position matches what was seen by observers on the ground as it left the Earth. So yes, that is the Falcon Heavy second stage, but we're going to do some more work with it here and use a simulator, orbiter spaceflight simulator, to actually simulate the launch. We did this once before. I did this a short time before the launch occurred, but I didn't really know what the flight plan was really going to be at that time. I knew roughly what it was going to do. It was going to put the second stage into an orbit that took it away from Earth and out as far as Mars, but we now know they did a burn to depletion where they basically used all their remaining fuel to throw that thing as hard as they possibly could out into the outer solar system. And it took it to an aphelion point, or a point furthest from the Sun in its orbit that is just past Mars's orbit. So yeah, that's quite cool. You can also see, well, I guess you can't see it on that screen, but I do have a link I'll put in the video description where you can see the orbit solution done a couple different ways. One giving heliocentric orbital elements, as well as the minimum orbit intersect distance, which is quite low relative to Earth, as you would expect, because that's where it came from. And there's been some studies done of the orbit that suggest there's about a 6% chance it's going to come back and hit Earth one day in the next few million years. Nothing to really worry about, but it's kind of interesting that it may not stay up there for billions of years, but maybe just a few million years. So, like I said, we're going to switch now to the simulator and simulate that flight once again, but now we know what the orbit was. We know that the orbit, according to official sources, got within about 190 kilometers at perigee and 7,000 kilometers at apogee, furthest point from Earth, before they did this burn. And so we're going to try to match that orbit, and we're then going to try to match the ejection burn and see if we can match it up to the orbit that I've actually calculated from my telescopic observations of the Falcon Heavy second stage. I've imported that data into Orbiter Spaceflight Simulator here. And so we're at T-minus 11 minutes now, and we're going to go ahead and simulate the launch once more, but this time we're going to try to fly it with the profile that the vehicle actually flew. And we're going to try to match that up and see if it really does match up with the orbital information that I determined. So there are a couple things on the map there. First of all, let me stop the recording now for sort of the overview of my observations and how we know this really is Falcon Heavy. But if you're just watching the brief summary, you can come back and see the replay of this live stream if you want to see the rest and how the simulation goes. Alright, so I've stopped the recording. That I'll upload as sort of a separate video summarizing the data from the telescope. But let's get into the simulation now here. So we have the map there, and it's a bit busy because we've got a couple different objects visible and being simulated. One is so we basically have two ghosts here that we're going to try to meet up with, or what I'm calling ghosts. Basically what I've done is I've taken the orbital elements that were the official orbital elements of the second stage when it was in its Earth parking orbit before it did its final burn, and I've loaded that into the simulator. I've also taken the state vectors from the orbit that I determined telescopically that corresponds to its trajectory after that final burn, and I've loaded that into the simulator as well and called that Tesla Deep Space. You can see it's there over the Pacific. And basically I've taken those orbits and propagated them back to a point in time shortly before launch. And so that actually shows the ground track for the initial parking orbit as a plus sign that's now somewhere over Mexico and coming towards us, and the ground track going over the Space Center, as you would expect, because we should be in plane with the orbit that we're eventually going to arrive in. The point here is to try to meet up with the initial orbit that they had. Now really they had an initial orbit for about 20 or 30 minutes that was a low parking orbit, but then they did a quick burn to put it in a higher orbit, an elliptical orbit that took it up to 7,000 kilometers, and that occurred before they started the Starman webcast. The Starman webcast then occurred while they were still in Earth orbit in this elliptical orbit that took them as high as about a 7,000 kilometer altitude. And that's about the time that they were over Australia, is when they were hitting that peak altitude, which is why you were able to see all of Australia and beyond. So we're going to take a look at what that looks like in the simulator by actually flying it in real time here. And we'll see. Depends on what you guys want, but I'm contemplating potentially leaving this stream up and the simulation up in real time to simulate the Starman webcast, just to show that it does match up with the simulator. I don't know. We'll see how it goes. If you guys, if it doesn't work out, or if you guys just want to skip to the end, maybe we'll time accelerate through that. But I'm kind of contemplating leaving it up for 6 hours and just showing, look, the Earth looked the way it did in the webcast here on the simulator as well, because, well, that's the orbit it had, and we're going to simulate that orbit. But we'll see. Maybe we can do a time-compressed version. Anyway, the external view... Oops. Why didn't that work? Oh. Hello? Oh. Well, that's a shame. Okay. I was supposed to have an external camera here that corresponded to my actual position watching the launch. I don't know why that didn't work, or rather why it went away on me. That's not good. I might be able to fix that. Shucks. Okay. Let me... for the moment... Yeah, I'll put DS9 back up. And... T... okay. Alright, so I'm going to put the actual images of the Tesla back up for a second. Sorry guys, I'm going to try to fix that camera so that I can show you the view that I actually had from the viewing site I had with the telescope, because I tracked the launch with my telescope. If you haven't already seen the video, please go check it out. It's the best video I've ever got of any launch, complete footage from launch to landing of the booster. But what I wanted to do is go in there. I need to fix that. Okay, so I'm going to try to reset the camera so that it shows the perspective I had at the launch site, where I was actually viewing it from. Okay. Okay. Let's just reset the camera there. Current state. Okay. Yeah, that should do it. Okay. Let's go back into Orbiter. Okay, cool. And that's zoomed in. Alright, so the graphics on this are not going to be perfect. In fact, it looks rather simplistic because I'm having to digitally zoom in here. Unfortunately, this is Orbiter 2016, and the telescope mod for Orbiter only works as late as Orbiter 2010. It's no longer compatible with the 2016 version. So I'm having to sort of do a workaround around that limitation. So let's see here. We've got our target set. Check the autopilot settings here. So yeah, we're going to end up in an orbit with a basically a circular orbit around 189 kilometers thereabouts. The boosters will automatically fly back and land. The center core will fly down and land on the barge. Sorry, autonomous spaceport drone ship. And hopefully be more successful than the actual center core was. The center core apparently had a problem where the fluid they used to ignite the engine, TTEB, did not last long enough. They didn't have enough of it for the final burn, and so the outer engines didn't start, only the center engine started, and it did not decelerate fast enough. And as a result, it splashed down in the water about 100 meters from the drone ship and actually damaged the drone ship in the process, hitting the water at about 300 miles an hour, from what I've heard. But in this simulation, things will go peachy keen, hopefully. So, tell you what, let's go ahead and time accelerate. We don't need to wait 5 minutes. We'll just skip right to the launch. Okay. I'm going to quick save it there. Alright. So this should track the way that my telescope did. Now the autopilot for this obviously was not written by SpaceX. This is written by a very dedicated modder who is really good at this stuff, and he wrote an autopilot that actually enables this thing to not only launch on its own at the with the parameters that you specify, but it even flies back and lands on its own. So the boosters pop off and they actually fly back to Cape Canaveral for their landing at the landing zone, LZ-1 and LZ-2, and the center core continues and then lands on the drone ship, just like the real one was supposed to do. But because he doesn't have access to the actual SpaceX software, flight software, the trajectory is not going to be a perfect match. The throttle settings are not exactly what SpaceX used necessarily, and the strategy for getting back to the landing site is not necessarily exactly the same as this strategy or trajectory that SpaceX used. But it's similar, very similar. And you'll notice it's pitching over already. That's what it's supposed to do to get to space. Some people think that launching straight up is how you're supposed to get to space, but no, that's not how you get to orbit. Orbiting the Earth is all about building up horizontal velocity. Most of your energy has to be put into a horizontal direction to build up more than 7 kilometers per second of velocity to orbit the Earth in your initial low parking orbit. And so, yes, it will pitch over pretty quickly if it wants to get to orbit efficiently. Flying straight up and then pitching over 90 degrees once you're in space is not the most efficient way to do things, that you will have huge losses there. The less time you spend fighting against gravity, the better. And so you can take a much more efficient trajectory by pitching over and gradually building up horizontal velocity. And you can see it's already going horizontal, and stage separation is coming up soon. I think it occurs a little sooner in this simulation than it did in real life, but again, the throttle settings were probably a bit different on the real vehicle. I know that they throttled down some of the stages during separation, and really seemed like they might have done that a few seconds before separation. In this one, you don't necessarily have to deal with that. It's not like you're ever going to have an issue where the aerodynamic forces cause it to self-collide or anything like that. Orbiter doesn't even really simulate collisions, but it doesn't matter. It works just fine. So there we go, there's stage separation, and the boosters are already heading back. I'm going to go ahead and keep it on the boosters. Just the way that my telescope video was, just so that you can see what that looks like here in the simulator. Again, I apologize for the limited graphical fidelity here. I'm digitally zooming in on the rendered screen, which is not the best way to do things, but since the telescope mod isn't working in Orbiter 2016, this is the only way I can do it at the moment. But graphical quality will get better once we switch to the second stage and start looking at it in space. So while we're waiting on the boosters to come back and land just like the real launch in the real video, let me take a look at the chat, see if anybody has any questions. Can I zoom in more? You could, but you'd just be looking at a couple square pixels basically. There's nothing I can do to enhance the detail, put it that way. So Ron asks, what imager do I use? That's a great question. So for itelescope.net, the telescope used and all of that, so it's really expensive stuff. It's Finger Lakes instruments, it's plane wave telescopes. The particular telescope and instrument I used was T27. Let's see, the model number on that is plane wave 27-inch 0.7 meter CDK 700 WF. It's a corrected Dahl-Kirkham astrograph. The camera was a Finger Lakes instrument PL 090000, which is an extremely expensive camera and an extremely expensive telescope for that matter. But yeah, really high quality instruments. The telescope itself is like a $210,000 instrument. Not cheap or affordable, but fortunately you don't have to buy the whole instrument. You can just rent time on it. And that's the nice thing about iTelescope is they've got telescopes in Australia, Spain, New Mexico, California. So throughout most of the day, there's telescopes potentially open somewhere as long as the weather's good. And if the weather's not good, you can just wait for the next site to open up. Now, the Tesla at this point is far enough in the southern celestial sphere that it's not really easy to get from more northern sites like Spain or even New Mexico or California. And even here in Florida, it only peaks currently at about 35 degrees over the horizon, and it's much too dim for my telescope at this point. But in Australia, it's high overhead and well positioned for T27. So you can see the boosters coming back now. Now, in the actual video, when I was tracking them, it was too far apart for my telescope to fit them in the field of view. Obviously, my telescope is a much higher magnification than this. But yeah, the landing burn as well might be a little bit different than it was in real life. In real life, they did I believe they did a 1-3-1 burn, meaning they initially turned on one engine, then they turned on 2 additional engines for harder braking, and then went back down to 1 engine right before landing. And so you can see the landing burn taking place here. Again, the guidance software here is not the official SpaceX guidance software. It's just a fan-made creation, but it works quite well. It does land successfully on the landing pad, so you can see the gear coming out, although it's a little pixelated. That's what's happening there. And then they touch down basically simultaneously. Boom. Beautiful. Okay. So let's switch now to the core stage. So now this is looking, let me turn off the zoom here. There we go. This is looking down the stage towards the engines of the core, and we're just going to watch it land here. How's the audio for everyone? I don't know if the audio is working at all. Can anyone hear the simulator with the engines burning or anything? It probably wouldn't be much in the way of sound at the moment, but David asks, when will Teletrack be released? It is released, or at least the pre-alpha is released. It's still in a very early experimental stage, but if you check back a few videos, there's a video about Teletrack pre-alpha release, and you can find a link there in the video description to that. Oh, I didn't know they... Oh, Vincent says that they do astronomy events at Bach Tower. That's Florida Attraction Gardens, I believe, here in Central Florida. I didn't know they did astronomy events out there. It makes sense. I bet they have... I bet they're far enough from Orlando that they get some decently dark skies. I don't know. I've never been out there at night. Audio is a bit soft. Okay, is it my microphone that's a bit soft, or is it the simulator? I mean, can you hear the engines right now? I don't know. Just did the entry burn on the simulator. I don't know if you can hear it at all. I mean, it doesn't much matter. There's not much sound, just engine noise, if anything. But you can see the drone ship coming up there in the ocean. Hopefully the landing's successful here. I did change the autopilot settings a bit to hopefully get it closer to the true orbit for the second stage, but I'm not sure if that's going to impact the core stage's ability to land or not. It should be okay. Looked like it was still well within limits. And unlike the real vehicle, there's no limitations on TTEB or anything. This simulator doesn't simulate TTEB or limited. I don't even think it simulates limited ignition. I mean, you can probably light the engine as many times as you like. There we go.
500, 400, 300.
Down now.
200.
Legs.
100. 50. 40. 30. 20. 10.
And a nice soft landing. How cool. Nifty neato. Alright. Now let's switch to the second stage. There we go. And now I've got a mod that actually puts a Tesla Roadster on the second stage. And we have not a completely accurate Starman, but a Starman nonetheless. So, let's see. I should have... Well, it doesn't much matter. I was going to say I should have taken note of when launch occurred, but I know when launch occurred. I set it for the actual historical time, which was 2045 Universal Time. So in 10 minutes it got us up to orbit, right where I wanted us to be. And actually, we're not too far away from the official orbit of the Tesla Roadster where it was. But we do have to do a burn to put us into an elliptical orbit. And according to a website I found, let's see, where is it? Come here. Here we go. According to spaceflightnow.com, at T plus 28 minutes 22 seconds, that's when the second ignition of the second stage occurred. That put them into the elliptical orbit, and it was just a 30-second burn. So let's see, I need to break out the calculator. It's too early in the morning for me to do math in my head. Okay, so that should be 13 minutes past the hour. 13:22. I should probably make a note of this. So it was at 21:13:22. That's the number we're looking for. Okay, so at 21:13:22, or about 16 minutes from right now, that's when the burn should occur to put this thing into an elliptical orbit, in theory. So let me bring up the orbit. Nice round circular orbit. Target, the Earth orbit version. Aha. That looks about right. So you can see the perigee distance of this yellow orbit matches the distance of my green orbit. This is the orbit I'm actually in right now. And in theory, these two lines, the green line sticking out from center and the yellow line sticking out from center on the left here, should come to the same intersection point when they reach perigee. I'm hoping you guys are able to see my cursor in the live stream. I don't know if you are or not. So let me just ask chat right now. Can you guys see my cursor moving around here on this left multifunction display here? Do you see a cursor here, guys? Let me check chat. Just want to make sure you guys can see my cursor. Don't know yet. You probably can't see it at the moment, but a moment ago you should have been able to see it. Anyway, okay. Hey Dick, how you doing? Alright, so I'm gonna assume that you guys can see it. I'm gonna go ahead and let's do this with maybe transix. That might be best. Target, planet, moon, escape, moon, none. Is it possible to do target another satellite? I thought it was. Ships. Here we go. Ah, right. Tesla EO. Ah, there we go. Okay, cool. So, hopefully, in 13 minutes, I can set this up. Maneuver mode 887. I need to break out the calculator. I have to convert that time into fractional day. Okay. 22 divided by 60 plus 13 divided by 60 plus 21 divided by 24 is 0.8843. That's the number that we want. Okay. That's curious. Oh, I'm doing outward. I meant to do prograde. Duh. Okay, wrong variable. That's why it was looking weird. Prograde. There we go. Yeah, so what we're trying to do is get this dashed line to match up with the blue line. Pretty simple. And what we're trying to do is set up a maneuver that will take us to about the same orbit as the actual simulated orbit. And even that has certain issues because I imported the elements at a point in time that they didn't actually exist. I mean, the thing wasn't in orbit yet, and I dumped it into the simulation. And so it's experienced certain perturbations that it never actually experienced, which has thrown it off course a little bit, I think. And perhaps out of inclination a little bit. Because it looks like it's at about 30 degrees inclination, which is not quite right. But whatever. I'll deal with it. So let's see. Variable outward. Kilometers. Okay, actually that's not bad. It's not bad at all. That's actually really, really good. So we're trying to get the close approach distance here down. How much time we got? About 10 minutes. Yeah, about 10 minutes. So we're going to use the historical burn time. Okay, that's as close. I mean, you're going to get perturbations that this program is not accounting. I mean, the TransX is not accounting for. This is a planning tool, and it doesn't account for all the factors at play here. So that close approach distance keeps changing. We kind of went over this in the Oumuamua webcast I did. It's the same thing going on here. So that's as close as you can possibly get it, and it's quite nice. So they will intersect here, and there's the slight out of plane component. I'm not sure I'll correct that. I might leave that alone because I think the out of plane component is artificial. The orbit I'm trying to reach, this is the official orbit that I've imported into Orbiter. But again, because I imported it in at a time that it wasn't actually up there, it's experienced certain perturbations that didn't actually happen, and I think that's thrown off things like inclination shouldn't be 30 degrees. It should be about 27 or 26 and change, something like that. So it's a few degrees off, but whatever, it's good enough. Point is, this will put us in the elliptical orbit that we want it to be in, and that's cool. So what we want now, okay, time to maneuver, yep, time to maneuver 462 seconds, yep. So we actually have to begin the burn at 4:35. So it may be a couple seconds off on that historical time at the start of the burn. But the timing of the burn, in terms of the duration, about 20 seconds, yeah, that's close. Or, it might be about, so it's time to maneuver 20 seconds from the beginning of the burn. Might actually be a 40-second burn. It's supposed to be a 30-second burn. Not sure. We'll see how long it takes to hit at delta V right there, 1.182 kilometers per second. And the remaining delta V is 6181 that you can see up here in the top left. So yeah, we got plenty of propellant for that. But I do want to wait till we're a little bit closer before using the RCS, because the second stage doesn't have a huge amount of RCS to play with. You can't just jockey this thing all over the place like you might want. It's only got about 100 kilograms of propellant for RCS. That's the maneuvering thrusters that allow the second stage to orient itself. Let's see, I should quick save this just in case. See, I just don't know if they had an out-of-plane component at all, and so I might. So I've got this out of plane, or it's not out of plane. I guess it's just outward, meaning pointing up a bit, to try to make this thing intersect as close as possible within a couple kilometers. I just don't know if that's really necessary. Let's see, actually. If I take that down, it kind of goes down towards the, kind of reduces it. Yeah, that outward velocity thing, that's a crazy thing. I mean, heck, if I get it within 10 kilometers of the actual historical official position or whatever this is telling me that position is, I think that's going to be good enough accuracy. The main thing we're trying to do here is set up the orbit to be the right elliptical orbit, so that when it comes time for the final burn, the orbit that I've calculated from my own telescopic observations of the object match up with what we're seeing here. We want to see if that really is the case, and it should be, but we have to set ourselves up properly with this elliptical orbit. So let's see, any last minute questions here before we do this burn? What is altitude when Starman camera comes on? So they popped off the payload fairing, and that's when they started playing that music, and you first saw the Starman right before they popped open the payload fairing there. During the webcast, I guess. Now, I didn't get to see the webcast live, obviously. I didn't get to see it till much later, as a matter of fact, because I was there, and I was filming with my own telescope. Now, and unfortunately, I don't think... darn. I'd like it if they would mod this so that they put the virtual cameras where they actually were on the car. They haven't done that for this mod. You can kind of move your camera around a bit, but it doesn't let you, quite move it to the historical, the true positions that it was at. But you can kind of point it, looking down the hood of the car like that a bit. but you're seeing the whole second stage here because the virtual camera position obviously is very separated from the second stage, and you can get it closer or further, but it's going to zoom in on the center of the stage. I don't have any mods to reposition that or anything, I don't think, so it's okay, we'll just deal with it. But okay, we've got 150 seconds now till the burn starts. Once we get within about 60 seconds or so, I'll start positioning the vehicle. I just don't want to do that before I absolutely have to, because the longer you spend trying to deliberately orient the vehicle, the more propellant you're going to burn on the pointing thrusters. I'm actually more concerned about using up too much fuel on the reaction control system than I am the main propellant, because I think we'll have what we need for that final burn. So yeah, it says I should begin the burn in 100 seconds. 2 minutes now. Yep. 2 minutes to burn. Yeah, that looks like it's going to get me right at about the historical time within a few seconds. Okay, says Sue says my audio is very low. Alright, let me try to boost. Oh, it's already at max. Sorry. My microphone's already maxed out. I'm just going to have to speak closer into the microphone. I'm also somewhat murmuring to myself here. Alright, so let's go ahead and point.
Translation.
Oops. Did I speak too soon?
Rotation.
I don't know why it's not letting my joystick do its thing. I wonder if the joystick control is not enabled for some reason. That could be. I'm not liking that. I'm not happy about that. Okay, so hang on a second. I'm gonna have to very quickly Control C. Joystick was disabled. That's why. Alright, sorry. Hang on a second, guys. Let's reset that. Fortunately, I did do a quick save earlier. If I have to go back, I burned a lot of propellant there using the autopilot. The autopilot is very hungry. It doesn't do things in the most efficient way at all, which is why I prefer to manually steer with this thing. Oh, and it crashed. Okay, orbiter completely crashed. Completely. Okay. I gotta reset the simulator. It just totally crashed when I tried to re-enter the simulation. Let's see. Let me see if I do the quick save. Okay. So I may have to fast forward time again a bit. Yeah, we're now back to 5 minutes before the burn. Sorry about that. Apparently the joystick wasn't enabled. It just shows you I didn't fly that launch manually at all. That was totally automatic. Okay. Alright, we'll fast forward now towards the burn. And let me make sure you guys are able to see everything. Yeah, it's all back and working. Okay, good. Just wanted to make sure. Okay, about a minute out from the burn now. So I'm going to go ahead and get this thing to point the right way. Accelerated a bit. Jeez, this thing's a bit of a slug. 10 seconds, come on! Pitch faster! Alright, there we go. 5, 4, 3, 2, 1, burn. And hold her steady. Okay, I overburned it a little bit, overcooked it. So the green is the actual orbit and the yellow is the target orbit. I let it burn a little too long. I'm going to see if I can try to trim it out a bit. I don't know. Probably shouldn't. Probably should just redo that, but I'm not entirely happy with my accuracy there, or lack thereof. Okay, now my apogee is about right, just under 7,000 kilometers. Periapsis 185. So let's go to docking, target, Tesla Earth orbit. Oh, fine. Sync orbit then. I just want to find out how far away I am from distance about 665 kilometers in closing from the historic position of it. It's not too bad. The big thing is the inclination, but again, I think that had something to do with the way the orbit imported. I just hope it's not that way with the hyperbolic orbit. The other concern of sorts is the RCS prop. I've already used about half of it. Eesh, that was not great. So let's see. Let's go back to Transix here for a second. Off maneuver mode, whatever. Target none. Target escape. Target. maybe it's because it's in system, it considers it not an escape plan, even though it's going to be a hyperbolic orbit. That's kind of interesting. Okay. There we go. Okay. So what you can see now is for the hyperbolic orbit, you can see how it comes in. It intercepts the green orbit, my orbit, right about here, and that's probably going to be where the burn is supposed to occur. Now let's go to the historical burn time. I should have that available. When did that occur? That occurred, so based on the orbit that I've calculated from the telescope observations, that was at 2:36 roughly, give or take a few minutes, or a fractional day. Fortunately, it shows that to me. So it's going to be February 7th, 0.1086. Okay. Let's go to maneuver mode. So now we're going to plot the maneuver for getting to getting to the Tesla's hyperbolic orbit. On 0.86. Okay, now in theory it should just be a prograde, pretty much to depletion. And depletion is going to be 4893 at the moment, but it's really a little less than that. 4893, I think, accounts for using up RCS prop on that or something. I don't know. It's gonna be close to that, give or take. So okay, that's interesting. That shows, what is the relative inclination there? It's about 2 degrees inclination. A little bit of inclination, a little bit more than I might like to see. Again, I think that's got something to do with the way the orbital element's imported into the simulator. I'm not terribly concerned about it, but so I think one factor is the historical time may not be exact. Because the slightest bit of misalignment of my current position is going to impact when that final burn should take place compared to when it actually took place. So again, we're trying to get the yellow lines to line up, the yellow dashed line to line up the blue line. Matches up pretty well. At least it looks like it does. Oh, great. I broke it. I done broke it. Ah, it did that glitchy thing again. I've seen it do that before. Okay, well, what we'll do is I will have to reset the program. Just give it a quick reset here. Hopefully this fixes it. To normal. Trying to see if the close encounter distance will stabilize at a reasonable number. I guess that's a reasonable number, but encounter velocity. It's quite high. Which, I mean, I'd expect it to be unless it was a burn depletion. Plotting this intercept is tricky, apparently. But okay. And encounter velocity is coming down. And goes back up. Reaches a minimum around there. Okay. So, let's see. The next thing I want to do, the webcast started at 21:39, so about 10 minutes from now, according to my calculations, based on the Elon Musk image and when that was in the webcast. According to the countdown clock or mission clock, that picture that Elon Musk tweeted out of Mission Control was at about 22:07 Universal Time, and that was a good few minutes into the webcast. And so if you do the math, it works out to the webcast start time being about 21:39 Universal Time. And at that time it was in sunlight, and you can see the sun is starting to come up over the horizon just now. So now the car is in sunlight. However, we need to, let's see, which way would it be? I don't know. Let's take a look at the map. So yeah, we'll be coming up on Australia soon, just like it was in the webcast. Trying to figure out which way to point the car to recreate the orientation that was present in the webcast. What I just don't know for sure, although I guess if I think about it, yeah. Okay, so right. I just need to look back at the webcast for a second and see what that orientation actually looked like in terms of north, south, etc. Okay, so it looks like, yeah, it looks like from what I'm seeing, the nose of the car, at least towards the start of the webcast, was kind of pointed towards the north. Yeah, that's what it looks like to me. So if I come back in here, I've got to be somewhat careful about propellant consumption. You can see where we are on the map here on the bottom right, in the center of the green circle. And let's see. Altitude 2,090 kilometers and rising. Let's just get an idea of where the nose is pointing. Right there is good. Alright, and now, let's see. I know I made a note about how, okay, it's one rotation every 6 minutes. From what I did some timings of the webcast, it looked like it, at least initially, was about one rotation every 6 minutes, so 60 degrees per minute, 1 degree per second. Seems reasonable. It almost sounds like a number somebody pulled out of their butt. Let's see, which way was it? It was spinning that way. Yep. Alright, so bank is now just about 1 degree per second, or 60 degrees per minute, if I'm reading that right. Looks like it's faster than that, but we'll see. Maybe it does take that long. I mean, maybe that is the right speed, I don't know. But one thing I want to do, I shouldn't have rotation in other angles. Yeah. Okay, kill it. I gotta kill it. Alright, let's try this one more time. That was too much. Still too much. That's just about right. Now, I don't know how the syncing is going to do, but the webcast would have been starting right about now. And by syncing, I mean I haven't started necessarily in the exact position that they started in the webcast in the rotation, so it may not sync up properly, but the general rate seems like it's about right. So there you go, the Starman webcast. Starting to come up over Australia. But we still got a ways to go before some of those iconic images really happened. About 15 minutes in. Well, it might have been visible. Okay, so sort of the day-night side, this whole Terminator that you're looking at right now, that was first visible about 10 minutes into the webcast. So we're getting an early preview of that. So again, the timing of how those events lined up, not necessarily going to be in sync with the historic timing, but yeah, not bad. Now I wonder, actually, I'm going to quick save. If I go to Tesla Roadster. Ah, there we go. Oh, that's much better. Now we can get a proper over the hood. So I just switched the focus to the Tesla. I should have thought of that sooner. Oh well, better late than never. So now I can get a proper side-on view there. I don't know, what do you guys want? Do you want side-on, over the hood, or sort of behind, looking through the windshield? Which angle do you guys want? That's rather nice, isn't it? Now again, the first few minutes of the webcast, you didn't necessarily see that. It was mostly just the Tesla with black. Well, I guess you did in the first few seconds, yeah. Backing up, going over the replay, yeah, you could see it coming into daylight. It was still just the sort of the crescent Earth over the windshield at 1 minute in. But then you didn't get to see it again for a while. Looks like Earth first came into view after that, like I said, about 10 minutes in. And that would have been at 49 after. So at 49 minutes, that's when you had this over the hood, looking over the front hood of the car, sort of at Starman's face, and you had the Day-Night Terminator in the background. And Australia was kind of up and out of the view. You didn't really see it there initially. But then a few minutes later, at about 15 minutes into the webcast, you had this nice side view of Starman and Australia. And he was basically directly over it at that time. So we'll see how that lines up here with the simulation. One thing I'll say for Orbiter 2016 is it has really nice graphics when it comes to Earth and space. At that 7-minute mark. So right at about 15 minutes in the webcast, it was kind of this really nice picture of Starman directly over Australia. So I'm thinking I'm going to accelerate to that point. And that point, let's see here, that would be what? 5402. Yeah, I'm going to go ahead and accelerate to that. So we're going to go to 215402 time code. Right there. Yep, high over Australia. Now, the rotation's not quite in sync, but it's actually not too far off. Except that we're on the wrong side. He was positioned, I think, like that. Yeah, we're 180 degrees from what it was in the webcast, but in general that was kind of the view you had. Also, the orientation I've got here is a little bit off, but you get the idea. High over Australia right there. That's pretty cool. Let's see what else we got. Alright, let's just see. I'm curious about the altitude. What is the altitude right now? 4,700 kilometers and climbing. So I'm kind of a mind right now of fast forwarding to the departure burn, but also kind of almost going seat of the pants on departure burn, because it really is just a pro-grade burn at the right time and the right speed. The real question is whether or not the orbit that I calculated for the Tesla will line up timing-wise with the simulated orbit that we've got going right now, where we simulated the launch and that first burn. Any inaccuracies in that burn that we did to try to match what historically happened is going to impact the timing of our arrival at the point where we should perform the departure burn. So we may have to do the departure burn a little bit sooner or a little bit later than what should have actually happened, if you see what I'm saying. So that makes it difficult to do it using TransX and sort of trying to do this intercept thing, because we're trying to intercept what I detected, yes, but not necessarily in the chase it down sense, more like the timing of the burn right sense, or at least as right as it can be. So I might use a different tool for doing this instead of, I don't know. Oh, it says no intersection. Oh, that's cool. I mean, they do intersect. They're just not, we're not perfectly in plane with our target, but that's basically an intersection right there. I don't know why it doesn't see that. South target. Yeah, it sees a relative inclination of 5 degrees, or 4.5. Isn't it degrees to intersection? I mean, it sees it there. That's funny. I don't know. I'm not familiar enough with the old transfer MFD. This is a built-in tool for helping intercept with other objects. The interesting thing and the good thing is it sees that intersection, I think. It's just maybe it's slightly out of plane. Maybe we're a little bit out of plane with what we're trying to intercept here. So that's throwing things off enough that it doesn't consider that a true intersection for sync MFD. I don't know. Giving kind of silly results there. It's probably because it's not designed to intercept with hyperbolic trajectories. It probably isn't capable of really handling that situation. Alright, so put in a fair bit of work here, but I finally got the encounter distance down pretty low. Encounter velocity not too bad. So let's go ahead and fire up transits on this side. Alright, there we go. Time maneuver 15,000 seconds. Or begin the maneuver and begin the burn. That doesn't sound. It's weird. That doesn't sound right. 3,000 second burn? It's 50 minutes. Oh, right. It thinks I'm driving the, yeah, it thinks I'm steering with the car. Alright, well, I'm gonna quick save it. Oh, please don't lose my transix settings. Please, please, please. Kinda lost it. Alright, we'll fool with that later. What I can do is I can hopefully transfer the transix settings from one to the other by doing a little scenario editing. Let's see, it's quick saves. Okay, yeah, there's the plan. Get him FD left, FD right. Okay, so for now, we'll just enjoy the pretty views. Yeah, the Musk image that he tweeted out would have happened a few minutes ago while I was fiddling around with all that. We're over 6,000 kilometers now. All right. So tell you what, let's go ahead and transfer back to the main stage. And what I'm going to do is I'm going to shut it down briefly here so I can transfer the orbit information back into the main stage. That. not save it? It did not. Oh, that kills me. It kills me. Why didn't it save it? Oh. Oh, it thinks... okay. I see why I didn't. I can fix it, I think. Yeah, Falcon Heavy. I just have to tell it you are there. Okay, let me try this one more time, sorry. Alright. Now, hopefully... No? No dice? No dice. Oh. Huh. Oh, I see. I didn't tell it the right name. Okay. Sorry. One more time. One more time. I just don't want to lose all the work I just put in trying to tune up that trajectory plan. No? Why not? Huh. Didn't save the maneuver for reasons unknown. It should have. Really should have. Maybe it goes like that. I don't know. More time. There we go. Alright, now we're in business. It was very persnickety. It wanted the spaces and everything to be accurate. Okay. Now I don't have to redo the maneuver. I'm happy. So... yeah, that's more like it. Now it's not telling me I'm going to have to burn for 3,000 seconds, because actually now I have an engine. The car is pretty much propulsionless, so it doesn't do anything. So yeah. Now we'll have no problem at all. In fact, I ought to be able to transfer. Yeah, I could transfer back and forth to the car and enjoy the view. But when I go back to the main ship, I'll have my trajectory already planned. How nice is that? That's weird. Why is it acting... Okay. I don't know why. for some reason it keeps showing my live stream health is not doing well. Do I sound okay? I don't know. Not sure why YouTube is reporting stream health as mediocre. According to OBS, I've got good stream health, and it's not having any trouble at all. So I don't know what's going on there. But okay. Chat's not reporting any problems, so I'm going to assume everything's peachy keen. Alright. Well, I tell you what, let's go ahead and transfer back to the main ship. We're going to go ahead and accelerate to the timing of the burn and see if we can intercept the orbit that my telescope calculated for the Tesla / Falcon Heavy second stage. So I'm going to quick save it one more time just for good measure. We have quite a while to wait until the burn begins, so I'm just going to keep accelerating. Hope I'm not making anyone too dizzy. Alright, cool. So, we're starting to get close. Close enough that you can see on the left here the blue line coming out from the center of the circles, extending this straight line extending to the hyperbolic orbit. That's where the calculated orbit or the observed orbit of the vehicle puts it at this time, and the green oval ellipse, that represents the current orbit that we have. We have to make it match the blue orbit. Now, it's interesting because I've got it set up to sort of chase down the actual detected position of the vehicle. It'll get within a couple dozen kilometers of it, which is really quite good. And you can see how the dashed line doesn't perfectly line up with the blue line, because we're basically not going to time it perfectly in terms of reaching the point where the burn should occur with the point that the calculated orbit puts it. So we kind of have to intercept it a little bit. It's close, but it's not perfect. And I kind of am not super surprised by that, because we manually flew this thing into the orbit that it's currently in. I manually steered this thing with the joystick, and I didn't do such a hot job of it, to be honest. It was kind of all over the place. But even doing it that rough, we're still on course for an intercept. And so that's what we're going to do. We're going to do the burn according to Transix, the way it wants, in order for us to intercept the detected orbit of the Tesla. And then when we reach that intersection point, I'll do a final short burst to basically drop us into formation with it. So the burn, let's see. 1,480 seconds. So yeah, the burn looks like it'll be about a minute long, roughly. It's going to be interesting. Now this time I'm going to start lining things up a little bit earlier than before because 60 seconds was clearly not enough. I really had to sort of accelerate the pitch over at the last second there, which is not ideal. And it looks like the burn will occur at about the right altitude that my calculated or detected orbit of the vehicle indicated it should be occurring at, which is cool because I didn't force that to happen. That naturally occurred because of the way that we launched it, because of the way that and the timing of the burn that put it into this elliptical orbit. It actually works out perfectly that you can see how the blue line here does come in and intercept with the green line right where we're going to perform that burn. So that's a very encouraging thing to see. So we're about 500 seconds out now. I'm going to go ahead and start pitching the vehicle down to get in the right orientation, and we're just going to wait for it here to line up with our desired burn direction. See, we're currently over the Pacific. I think we're basically going to be over Mexico when the burn occurs. However, this big green circle around on the map, or it's not really a circle, but whatever that is, that big green line that encircles us, that's the line of sight. Anyone within that range has line of sight to the vehicle. And although we're in daylight, I should point this out too, although we're in daylight right now, the dark portion of the map is not in daylight. The sun's blocked for that portion of the map. So people have line of sight to the vehicle right now who are actually on the night side of Earth and in America, California, Southwest US. Okay. Yaw it this way a little bit. So yeah, I think it's possible that the burn actually occurred when the vehicle was in daylight. I don't know that for a fact, but we're about to find out, and that would explain also why the cloud that was seen by people was so bright. If that thing was lit up by daylight while they were, you know, experiencing darkness and on the night side of Earth, that would definitely do the trick in terms of putting on quite a display for people. Alright, we're basically at the burn attitude, so we're just going to hold it here for the next 6 minutes while we wait for the burn time to come up. We are approaching the day-night terminator, so it may go into darkness here. It may not have been lit up by the sun. We'll see. But yeah, this is the actual pointing direction the vehicle would have been in roughly during that final burn. Now I think they probably just aimed it prograde, but we're not too far from that direction. We're a little off kilter here because we're going to intersect. We're actually burning in a direction that's going to intercept us with the historic orbit, or the true orbit that was detected of the vehicle. And because of the rough way that we flew this thing into the current orbit, it's not going to involve just a simple prograde burn. I think there's also some issues with the way that the state vectors were imported into the program. I'm kind of wondering if maybe the state vectors that were exported by FindOrb were in a different epoch than the state vectors that Orbiter 2016 is expecting, because I don't think Orbiter even Orbiter 2016, I don't think it accounts for precession. So that may cause some slight inconsistencies. Now we'll time accelerate into the burn, because we're basically ready. So you can see the prograde marker down here in the bottom, that plus sign with a circle around it. That's the prograde direction. Okay, 1 minute. 30 seconds. I'll go ahead and save it one more time, and now we'll tune up our pointing direction here. It's 5, 4, 3, 2, 1, 0. Burning. Alright, engine's on full. You can see on the left our orbit's expanding as we burn prograde here. See if I can trim out a little bit of the excess delta V. We've got about 13 meters per second off the mark, which isn't too bad, but it could be better. I'm so used to playing Kerbal Space Program with the realistic progression mod, so that the engines, most of the engines in the game, don't have throttle ability, because in real life, most spacecraft main engines don't have the ability to throttle. They're fixed throttle, and Orbiter is very forgiving about that. They let you throttle it. Any typical Orbiter ship, you can throttle any setting you want, which makes it easier for sort of simulation purposes, but not necessarily the most realistic. However, there are realistic mods for Orbiter that do force you to use realistic throttle settings. Anyway, sometimes I forget that I can actually drop the throttle a little bit. Okay. Yeah, we think we overcooked it a bit. Just get that crosshair close. Starting to run a little low on propellant for the maneuvering. Ah, shoot, I overcooked it the other way. Okay, we'll call that good enough. Man, all I did was tap the throttle, and that was too much. Okay, we'll turn off maneuver mode. So we'll get within a few hundred kilometers of the desired position. So yeah, actually that whole burn did occur in daylight, and as you can see, we are over southwest United States and Mexico, and that is where the burn was observed, including from the MMT Observatory in Arizona, which is the all-sky webcam I showed you at the beginning of this webcast. We saw that, and you could see it passing to the south and low over the horizon, because Arizona would be up there somewhere. And yeah, it was illuminated by the sun, which is why that cloud was so bright. And that webcam, that all-sky cam, was quite sensitive. But even so, observers saw it by eye quite clearly. I'll show you that one more time, just for anyone who joined late. So this was that all-sky camera, and you could see the second stage coming into view there. Skip it ahead a bit. So the burn would have begun somewhere right around here, right at about 7:31 local time. That was, again, 9:31 like Eastern time where I'm at, and that was 2:31 Universal time. And there, it's passing out of the field of view, and the burn is complete. So right now it actually is 2:31. So this right here was the historic time of the burn. It would have been back further off in the west. And if I look at the orbits here, we've already passed the point where the burn occurred. Obviously, we've already completed the burn. But if you look at this blue line coming out here from the center of Earth, extending out to the hyperbolic trajectory, that is the detected orbit of the object. That's the orbit that I've calculated for it. And you can see it's approaching its closest approach to Earth right there. So it is actually closer probably to the true historic orbit than what we just flew sort of manually. But we're close. We're within a couple minutes of the historic time. Oh, wait, you guys are still stuck on viewing that MMT thing. Let me go back here. Let's see. There you go. So, once again, sorry. If you look at the, well, either of these MFD windows here, you can see a blue line extending from the center of the circle to the curved line. That's the orbit or hyperbolic trajectory heading away from Earth. And you can see that the blue line represents the detected orbit, the orbit that I calculated based on telescopic observations of the second stage over the last 8 days, and projecting that backward and putting it into the simulator here. You can see it's passing its closest approach to Earth right there. That's when the burn would have occurred, and it would have put it into this orbit. And that timing, you can see up at the top right corner, we're now reaching about 2:33 Universal time. That was just basically just after the burn occurred. So the detected orbit that I calculated from observing it actually matches a little bit better with the webcam footage than what we just flew sort of manually. But it's close. It's within a couple minutes. And so we will actually get even closer to it because of the trajectory that we flew. We'll actually get within a few hundred kilometers of the true position of the vehicle based on my own observations of it. And if this were Kerbal, I would just turn on the nav bar or nav ball to target relative velocity and kill that velocity. Can't quite do that, but there is a similar function here. So relative velocity there to target. Oof, at the intersection. Yeah. It's all screwed up because it's hyperbolic. It doesn't really like that, does it? Let's see. I don't think this is going to work either because it doesn't have a docking port, so it doesn't let me. Oops. And I probably just crashed it. I crashed it. Okay, that was not good. Oh no! Oh no, I crashed the program. Okay, well that's not good. Let's not hit that button again. Oof. I goofed that up real good. Oh no. Oh boy. It didn't save. Oh, it kills me. Okay, well. Shoot. Oh, I didn't save it. It just crashed it right away. Alright, well. That's a bummer. For anyone who wants to watch the burn again, I have to redo it. Alright, I'll skip ahead here as quick as I can. And won't be quite as careful about it this time, I guess, but try to redo what we just did. Oof. Did I mention that Orbiter's free, so, you know, can't really complain about the product. It is free, and it's basically one guy's creation, so if there's the occasional bug here or there, I'm willing to overlook it. 3, 2, 100, okay. One advantage of Orbiter, though, over Kerbal Space Program, at least with Transx, well, there's lots of advantages, but one of them is it calculates for you your burn time, I think, a lot better than Kerbal Space Program does. I know Kerbal's supposed to have this function where it kind of estimates how long you're going to burn for, but for me it never seems to work. Oh no, oh gosh, I goofed it up. I goofed it up. I used up all the propellant. Okay, we're gonna cheat. Alright, I give up. I'm gonna cheat. I don't care. If anyone wants to fault me for cheating, well, too bad. I'm tired of dealing with this. Propellant. We're gonna... Let's see. This is... Okay, this is... Okay. Haha. I refilled the propellant. Alright. 3, 2, 1. Burn. See, the engine does gimbal. You get a lot more control authority once the burn starts. So what I did there is I refilled the RCS tanks. Yeah, it's cheating, but who cares? It doesn't actually affect the overall capability of this thing to reach a certain velocity or a certain trajectory just a few meters per second, really. There's not much fuel there. Alright, at the end of this burn, I'm slowing down the throttle so that I hopefully don't overcook it as bad as I did last time. I say that right as I'm about to overcook. Yeah, actually that wasn't as bad as last time, but let's try to trim it out a little. See that little. Just trying to clean up the burn, as they say. There we go. Fraction of a meter per second difference. That's what we want to see. Okay. Maneuver mode off. Alright, so we're back where we were. Alright, now let's time accelerate one more time. And just for good measure, at the end of that burn again, the second stage is in sunlight, but it's got plenty of line of sight to a lot of Southwest America, which is why I put on that beautiful display lit up by the sun as it was doing that final burn. So let's go ahead and accelerate to that intersection point. So this does tell me my relative velocity right now. What I don't know is which way I need to burn to halt that velocity. We'll do things the old-fashioned way here. Okay, that's the wrong way. And yeah, as far as I know, the Tesla was never supposed to be released from the second stage. It just remained with the second stage the whole time. Oh, that's really the wrong way. Okay. I just love trial and error. Just love it. There's probably a better way to do this. I know there's got to be a better way to do this. I just don't know what it is. Okay. That's bringing relative velocity down a bit. there we go. That's actually pretty good. So we've lined up the orbit, and we are basically in orbit with what I believe to be the detected orbit of the Tesla. I say believe because I need to make sure that it actually did import properly into the program. Didn't really have time to verify that. So we will see here shortly. If I just go to Transx actually, and I go forward, okay, maybe it doesn't, you don't like that, okay, let me just save it just in case. Should have learned that lesson before. So instead of a target, we'll do no target. Right. Escape. Forward, none. There we go. Planets, targets. Mercury, Mars. Perfect. There we go. Yeah, that looks right. By that I mean it goes to the orbit of Mars, just a little bit beyond, and then crosses it again on the way back. Now what's interesting here, and this is why I bothered to go back and redo that burn after it crashed, I'm noticing something kind of interesting, which to me is curious, very, very curious. What do you guys see here? I see remaining delta V 1,870 meters per second. Now, there could be a number of reasons for that. One, it's possible that the Roadster plus its adapter and the cameras and the Spaceman, although I don't think the Spaceman added very much mass, but maybe there was more mass on the Roadster than just 2,000 kilograms. The Roadster by itself, according to Wikipedia, weighs 1,300 kilograms. And the mod puts it at 2,000, which I guess adds some allowance for the adapter plate and all this stuff up here that's holding it in place. But if the true payload mass is higher, and I know they had a couple secret payloads, but I don't think they weighed very much. I don't think they have much mass. But if the true mass were higher, then what we should have left of the delta V should be lower. From what I heard, from the way Elon Musk put it, they did a burn to depletion. That means they used every ounce of fuel they had left. If I had used every ounce of fuel I had left, I would have a much bigger orbit that would take me out to the asteroid belt. But this is the detected orbit, basically. We've now intercepted the orbit of the object that I detected. And our distance is currently 400 kilometers. That would come down. I could let it intercept it at an even closer distance and then drop that relative velocity right down to 0. I'm not going to bother with all that. It doesn't much matter. A few hundred kilometers here or there, not going to really matter. At the kind of distances we're talking about, the pictures I just showed you at the beginning of this webcast, the pictures I took with the telescope earlier today were at a distance of 2.9 million kilometers. At that kind of distance, a few hundred kilometers here or there, it doesn't much matter. But the overall trajectory is correct. We reached that trajectory. And we reached that trajectory, and here's what surprises me, with a lot of fuel to spare. Let's find out what the fuel mass is. That tells me, so we have that much fuel in terms of delta V budget. How much fuel is it in terms of mass? Is that 4,000 kilograms, or is that 4? Can't be 4 kilograms. Where's my scenario editor? I'm not going to edit it. I mean, I'm not going to change it. But I am going to look at it. What is the propellant level? I only refilled the RCS prop. That's just the reaction control thrusters, not the main propellant. So we have 4,125 kilograms of fuel left. I mean, that's not totally insignificant. Percentage-wise, it's about 3.8%. I mean, it's not a huge amount, but it's not insignificant either. You get the most bang for your buck out of your last few drops of fuel, because the vehicle is at its lightest, and so the thrust is doing you the most good. It's giving you the most change in velocity for your fuel. When you're fully fueled, you're carrying a lot of fuel, so the vehicle is very heavy, so it doesn't accelerate as much per second. But in those last few seconds, when you're burning the last bit of your fuel, you're getting the most acceleration you're going to get. So 4%, not much. It's actually less than 4%, but still, it ends up giving you a high delta V left over 1.8 kilometers per second. That's not a small amount. And that's surprising to me, because we did everything right in terms of putting it in its initial orbit, putting it in elliptical orbit, and it reached the right altitude when the burn occurred. It was about, I didn't check it precisely, but it was about 600-700 kilometers in altitude when that final burn occurred. And so you're going to get the right amount of Oberth effect. The Oberth effect, you get more bang for your buck when you're closest to a planet doing your burn than when you're far away. So those factors were all pretty much accounted for. The only thing that wasn't was the true mass of the payload, maybe. But that just surprises me that there's that much left over. So does that mean that they didn't actually do a burn to depletion, or something went wrong with the burn to depletion? That's speculation. That's really maybe reaching. A more reasonable explanation might be the fact that the autopilot for the initial launch was more efficient than the trajectory SpaceX actually took. Maybe it pitched over a little faster. Maybe the fact, and it's probably this is probably a part of it, the fact that the boosters may not have throttled down the way they actually did on the actual launch to make stress levels lighter on the vehicle. This mod does not simulate stress on the vehicle. It doesn't simulate the vehicle shearing itself apart if it releases those boosters at too high a thrust level. It just doesn't account for any of that. And so that simplification may have resulted in the vehicle being given more boost by the boosters. It may have been at a higher velocity when booster cutoff and separation occurred. And that may give the second stage more fuel, essentially, because it doesn't have to do as much work to get where we are. So that's a very possible explanation for why it was the way it was. The other thing I didn't check, I just loaded up this mod. This is a mod for the Falcon Heavy mod. It's like a mod on top of a mod that adds the Tesla. But what I didn't check is the position of the drone ship. Because another thing that happened, my understanding, is the core stage performed a boost back burn as well to sort of kill its velocity, so it didn't have to go even further downrange to land on the drone ship. I don't know how much killing of velocity it did in this simulator. Didn't really take a close look at that. I'm assuming that the mod put the drone ship in the historic location, but I didn't check that myself. Let me see if I can check that. Okay, landing pad, barge. Ah, here we go. I wonder if I can find out. I wonder who would have that information. What I want to find out is where the barge actually was. What were its coordinates? Chat, can you guys, I don't know if anyone's still with me at this hour. Yeah. I don't know, Bodie or somebody, I don't know if you guys can look up the coordinates of the barge, or the, sorry, I keep calling it a barge, I know SpaceX doesn't like it being called barge. Autonomous Spaceport Drone Ship. Where was the drone ship on the Atlantic? STS, Falcon Heavy, coordinates. I need to know. Okay, here's NASA's space flight. I'm sure it's out there somewhere. Somebody's got to know what it actually was. this is an older thread. I know somebody's got to know what that was. Falcon Heavy, let me put that in quotes. Of course, I still love you. Here we go. Okay, drone ship coordinates for FH core attempt. Okay, now this is just some random poster on NASAspaceflight.com, so I'm hoping what they're saying is accurate. I'm going to assume it is for a second because I don't have any other information. Let's see, where is it? ASDS 77 point, yeah, okay, so in the simulator it was at 77.132 west and 29.006 north. According to this poster, it was at 29.0055 north and 77.1319 west, basically the same position. So yeah, that wasn't the issue, or at least that wasn't a factor. So the core would have performed the same boost back burn and landing burn that would have really tried. Now, I don't know if it did a full, I don't know if it did I didn't catch it. I'm sure it's in the stream somewhere, but I don't know if it did a full 3-engine landing burn and really tried to save its fuel. If it had, that would have meant it would have used more fuel on that initial boost of the second stage. It really all comes down to what was the second stage's velocity when the first stage cut off, or the core stage cut off and separated from it. And we didn't catch that during the stream. But I can't imagine it was all that much faster than it was in real life, especially if it wasn't doing a 3-engine landing burn. Maybe it was, I don't know. But even if it was, I mean, I don't know, it's boggling my mind right now. Why is the delta V remaining that high? The only other possibilities I can imagine. That is a possibility. I hadn't considered one thing that the simulator is not taking into account that would be an issue in real life, and that is boil off. The second stage, like its first stage counterpart, uses liquid kerosene, but it also uses liquid oxygen as an oxidizer. It's got to bring its oxidizer with it. That liquid oxygen is obviously very cold, cryogenic propellant, and it can boil off. Some of it can be lost just because it's sitting in orbit for 6 hours. And so I know they were concerned about fuel freezing, but they also probably may have lost some of the liquid oxygen to just boil off. And if that's the case, that would lower their total delta V available. It's like basically you don't get as much fuel as you actually launched with. In the simulator, there is no boil off simulated whatsoever, and that would explain it. Probably that's probably the biggest source of discrepancy between the simulator and real life. There's also pre-chill that they do, where they basically start circulating some of the cold propellant through the engine before they fire it up, so that it's already at the right temperature so that they don't burn up the nozzle. And obviously that's not simulated, so you don't have any losses there. I think that's probably the biggest source of it, though, is just boil off. I bet that's what it is. And yeah, there's 4,000 kilograms remaining according to the simulator, but, you know, something like half of that is going to be kerosene, which isn't necessarily going to boil off, but the other half is going to be liquid oxygen. That's potentially going to be lost to space, I guess, if that's really what it is. I mean, yeah, 4%, little less than 4% fuel. Yeah, maybe they consider that acceptable loss, I guess. I mean, it was sitting in orbit for like 6 hours before they did that final burn. That's just interesting to me. That's why I wanted to really finish this out, to see that, yeah, in the simulator you could go further by a lot, but in real life maybe it doesn't really work out that way because of issues with the boil off. I'd just really be curious to see if that's the case, or was there something else going on, something that they didn't quite get as much performance out of the engine as they should have. But I don't think that's the case. They talked about it being within like a half sigma of their predictions or something like that during the press conference. I don't think they're just making that up. But I do think that boil off is an issue that the simulator is not accounting for. It'd be fun to crunch some numbers and see what's reasonable for that. I don't know, chat, you guys got any other ideas? Bodie McBoatface asks that I mentioned the secret payload. Any speculation as to what these may have been? Well, there's some people talking about the secret payload as the Ark. There's a data disk sitting on the Tesla storing information that's supposed to be able to last for millions of years or something, uncorrupted. And they put the Civilization, or the, what was it, not the, I keep calling it the Civilization series. It's what is it? It's that Asimov book or whatever. It's the one he names all of his ships for. Culture. I keep calling it Civilization. I don't know why. Culture series. I think they put the Culture series on that disc. That would make sense anyway, but I should probably check and make sure I'm not misspeaking here. Tesla Ark data. I am misspeaking. It wasn't the Culture series, sorry. It's Asimov's Foundation book series. These names are all too much alike, but yeah, no, they did put some data on the Roadster in case someone should find it. They also put a nameplate on the payload adapter with the names of SpaceX's employees inscribed on it in very, very tiny font. I imagine that's not going to last very long. Micrometeorites will probably take that out in a few thousand years, but hey, whatever. It's cool to have your name up there, right? And there's also a plaque that says something like built on Earth by humans. So there's all these neat little Easter eggs, I guess, riding around with the car. But I don't know if that's really the secret payload. I thought they might have some sort of... my speculation is they do have some sort of science payload on there, but they didn't want to make a big deal out of it in case the thing blew up. I don't know, is there any news about that secret payload? No, okay, so the only thing they're saying about the secret payload is that it is the Ark. Tiny storage device, holding libraries of information encoded on a small disk of quartz crystal, not much larger than a coin, etc., etc. Can theoretically hold up to 360 terabytes of data, about as much as 7,000 Blu-ray discs. Cool. So that's all neat. It is a bit of a shame that they couldn't put any more science payloads up there with it, but I mean, I understand from a certain PR point of view, if the thing went south and blew up, you just know there would be a ton of articles criticizing SpaceX for killing some poor student's science project. You know, that just, there's no getting around that. And so perhaps, I guess, they made the evaluation that it'd be better just to launch the mass simulator alone and not risk any student's payload, even if they were willing to sacrifice their payload to the mission, just because for PR reasons it wouldn't look good if it didn't go right. you know, and then, you know, there's just the issue of also trying to keep the mission as simple as possible. Don't add any complications of things you have to deploy, things like that. The less moving parts, the less that can go wrong, the better. I mean, then again, putting a few HD cameras on the car and transmitting the data down, all that cool stuff, that doesn't sound completely complication-free either, but it all worked out in the end, and I think it was a brilliant, inspirational PR stunt. I mean, yes, it was a PR stunt, but it was something that I found to be quite beautiful to behold and inspiring. So it's definitely, you know, just something you can relate to, seeing a human-sized figurine in a car. It's your everyday experience in a very abnormal setting, flying above Earth. So I think it was a great event, and I'm really glad I got to be there for the launch, and I'm glad, very glad, I got to track the spacecraft in deep space. So yeah, it'll continue flying out there for at least the next few million years before it runs into something. So before I close it out, I guess I'll just put it up there one more time. There it is, the actual vehicle, the Falcon Heavy second stage with its Tesla flying in deep space earlier today, taken with a 0.7 meter telescope in Australia. It's fading fast. Within the next few days it'll probably drop below the magnitude that even that telescope can achieve, and so the only scopes left that will be able to get it will be professionals. It's already approaching magnitude 20 thereabouts at this point, which is extraordinarily dim, many times dimmer than anything you can see by eye, of course. And even the first images I took 8 days ago, it was already magnitude 15 or thereabout. I mean, you wouldn't see that in most amateur telescope eyepieces. You really needed a CCD camera to pick that up. It was about the same magnitude as the Central Star in the Ring Nebula, which is a quite dim target. If you can see that with your eyepiece, you've got a good telescope. So, yeah, it is dim. People see these pictures I show and they think, well, how can that possibly be? I mean, it's so far away. It is, and sunlight is reflecting off of it all the time. And that nice bright white second stage is a nice reflector of light. And the Tesla is still attached to it, so most of the light we're seeing there is probably coming from that second stage, I'm guessing. I haven't done the math on that, but it would make sense. Even so, it's really cool to see it out there that far away, almost 3 million kilometers in those pictures. So it's out there. The trajectory matches the second stage of the Falcon Heavy in every possible way. The inclination matches the latitude of the launch site. The distance of it when it was close to Earth matches what we just saw, flying it ourselves and trying to match the orbit as best as possible. It all works out. It ends up in that same trajectory, going out just past Mars and then looping back. So there's no doubt that is it. That is the Falcon Heavy second stage. So I will upload the summary I did at the beginning of this webcast as a separate video later, but I hope you all enjoyed this webcast. Let me know in the comments section if you have any other suggestions for what I can do with this kind of thing in the future. Oh, and I have a question here from Code Phoenix. He said he was 40 feet away from me at the Falcon Heavy launch. Did I enjoy the traffic when leaving? Averaged 20 miles an hour all the way back to Orlando. Well, fortunately I didn't have to go as far as Orlando, but yeah, that was fun. It took me almost 3 hours to get back to where I was staying, which was only supposed to be 20 minutes, maybe 30 minutes away. So yeah, that was hellish traffic getting out of the Falcon Heavy launch, but you know what? It was completely worth it. And I honestly expected that going in, that the traffic was going to be good. So yeah, Loopy Dragon, he was there too. I remember I met him at the launch. I met a couple of you guys at the launch. So I'm glad you guys were able to make it for this really early morning webcast here. But yeah, I mean that's so cool to be able to see that and then be able to see it in deep space afterwards. Really neat stuff. Not every day do you get to see a privately made spacecraft beyond Earth orbit just because they can. In fact, that's the first time that's ever happened, that a private company has launched their own private payload into a hyperbolic orbit for basically no reason other than let's just test it and see if we can. So yeah, that'll do it for this webcast. Thanks for watching, guys. Clear skies, folks.